What if everything you thought you knew about reality was just one tiny piece of an infinite puzzle? Picture this. Somewhere out there, in the vast expanse of existence, there could be another version of you living a completely different life, making choices you never dared to make. This isn't science fiction, it's the mind-bending concept of the multiverse. Today, we're diving into 25 fascinating theories about how these parallel universes might interact, collide, or even influence one another. From the quantum realm to cosmic strings, from black holes to holographic projections, we'll explore ideas that stretch the limits of imagination and challenge our understanding of reality itself. So, buckle up and get ready to journey through the mysteries of the multiverse, where every theory opens a door to a new dimension of possibilities. By the end of this video, you'll not only have a deeper appreciation for the universe or universes we live in, but you might just start questioning what's real and what's possible. Let's begin. Now turning to the first theory, let's explore how quantum mechanics hints at the existence of parallel universes through a fascinating concept called superposition. At the heart of quantum mechanics is the idea that particles can exist in multiple states at once until they are observed. This might sound strange, but it's the foundation of one of the most famous thought experiments in physics, Schrödinger's cat. Imagine a cat placed in a sealed box with a device that has a 50% chance of releasing poison. According to quantum mechanics, until you open the box, the cat is both alive and dead at the same time. This bizarre scenario illustrates superposition, where multiple possibilities coexist. But here's where it gets even more intriguing. Some scientists suggest that each possible outcome doesn't just exist as a probability. It actually happens, but in a separate universe. So, in one universe, the cat is alive, and in another, it's dead. This idea implies that every quantum decision, no matter how small, could spawn an entirely new universe. It's a mind-blowing concept that challenges our understanding of reality and opens the door to the possibility of countless parallel universes, each branching off from every possible quantum event. As we move forward, we'll see how this theory sets the stage for even more astonishing ideas about the multiverse. Now turning to the second theory, let's dive into Hugh Everett's many worlds interpretation, a groundbreaking idea that takes the concept of superposition even further. According to this theory, every quantum decision doesn't just create probabilities, it actually splits reality into multiple branches, each representing a different outcome. Imagine you're flipping a coin. In our everyday experience, it lands on either heads or tails. But in the many worlds interpretation, both outcomes happen, just in separate universes. In one universe, the coin lands on heads, and in another, it lands on tails. This means that every time a quantum event occurs, the universe branches into multiple versions of itself, each one carrying forward a different possibility. This theory helps explain why quantum events seem so random. What we perceive as randomness might just be our limited perspective, unable to see all the branching universes that exist simultaneously. For example, when a particle appears to randomly choose a path in a double-slit experiment, the many worlds interpretation suggests that it doesn't choose at all. It takes every possible path, but each path exists in its own universe. This idea not only challenges our understanding of reality, but also raises profound questions about the nature of existence. If every possible outcome happens somewhere, what does that mean for free will, identity, and the choices we make? As we continue, we'll explore how this theory connects to other mind-bending ideas about the multiverse and its interactions. Now turning to the third theory, let's explore the fascinating concept of bubble universes in cosmic inflation. This idea suggests that during the rapid expansion of the early universe, known as cosmic inflation, pockets of space could have formed their own distinct regions or bubbles, each with its own unique set of physical laws. Imagine the early universe as a pot of boiling water with bubbles constantly forming and popping. In this analogy, each bubble represents a separate universe expanding and evolving on its own. These bubble universes could exist entirely independently of one another, with no direct interaction or overlap. Some might have stronger gravity, while others could have completely different fundamental forces or particles. This means that the laws of physics we take for granted in our universe might not apply in another bubble universe. For instance, in one bubble, light might travel faster or time could flow differently. The idea of bubble universes also ties into the concept of eternal inflation, where the process of cosmic inflation never truly stops. Instead, new bubbles continue to form endlessly, creating an infinite multiverse filled with countless universes, each with its own unique properties. This theory not only expands our understanding of the cosmos, but also raises intriguing questions about the diversity of reality. What would it be like to live in a universe where the rules are completely different? As we move forward, we'll delve deeper into how these bubble universes might interact or fail to interact with one another, and what that means for the broader multiverse. Now turning to the fourth theory, let's dive into the intriguing world of string theory and the concept of branes. String theory is a framework in physics that attempts to reconcile quantum mechanics and general relativity by proposing that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe in our universe. But string theory doesn't stop there. It introduces the idea of branes, short for membranes, which are multidimensional objects that exist within higher dimensional space. Think of a brane as a sheet or surface that can have multiple dimensions. Some theories suggest they could have up to 10 or even 11 dimensions. These branes can move and interact within this higher dimensional space, and when they collide, the energy released from such a collision could be enough to create an entirely new universe. Imagine two massive sheets floating in a higher dimensional space, slowly drifting toward each other. When they collide, the impact generates an enormous amount of energy, sparking the birth of a new universe. This process could explain how our own universe came into existence, as well as how other universes might form within the multiverse. The idea of brane collisions also opens up fascinating possibilities for the structure of the multiverse. If branes are constantly colliding and creating new universes, then the multiverse could be a dynamic, ever-changing landscape, with universes popping into existence like bubbles in a cosmic foam. This theory not only provides a potential mechanism for the creation of universes, but also suggests that the multiverse could be far more interconnected than we previously thought. As we continue, we'll explore how these interactions between branes and universes might shape the broader multiverse and what it could mean for our understanding of reality. Now turning to the fifth theory, let's explore the holographic principle, a mind-bending idea that suggests our universe might not be what it seems. According to this principle, everything we perceive as three-dimensional reality, stars, planets, galaxies, and even ourselves, could actually be a projection from a two-dimensional surface. Think of it like a hologram where a flat image creates the illusion of depth and complexity. In this case, the flat image is a higher dimensional surface, and our universe is the holographic projection. The holographic principle emerged from studies of black holes and quantum gravity, where physicists discovered that the information about everything that falls into a black hole is encoded on its surface or event horizon. This led to the idea that the universe itself might operate in a similar way, with all the information about our three-dimensional reality stored on a two-dimensional boundary. If this is true, it would mean that our universe is essentially a cosmic hologram, with every event, particle, and interaction encoded on a higher dimensional surface. But what does this mean for multiverse interactions? If our universe is a holographic projection, it's possible that other universes could also be projections from their own higher dimensional surfaces. These surfaces might exist in a shared higher dimensional space, allowing for interactions between universes. Imagine multiple holograms projected from different surfaces, overlapping or influencing each other in ways we can't yet fully understand. This could provide a framework for how universes in the multiverse might communicate or interact, even if they appear entirely separate in our three-dimensional view. The holographic principle also raises fascinating questions about the nature of reality itself. If our universe is a projection, what lies beyond the higher dimensional surface? Could there be other layers of reality, or even other holographic universes existing alongside ours? These ideas challenge our understanding of space, time, and existence, opening up new possibilities for exploring the multiverse. As we continue, we'll delve deeper into how this principle could reshape our understanding of the cosmos and its interconnected nature. Now turning to the sixth theory, let's explore the concept of cyclic universes and eternal recurrence, a fascinating idea that suggests the universe might not have a single beginning or end, but instead goes through endless cycles of expansion, contraction, and rebirth. This model proposes that our universe is just one in an infinite series of universes, each born from the collapse of the previous one and destined to collapse again, giving rise to the next. It's like a cosmic heartbeat, with universes expanding and contracting in a never-ending rhythm. In this cyclic model, the Big Bang isn't the beginning of everything but rather a transition point, a moment when a previous universe collapsed and rebounded into a new one. This process could repeat indefinitely, with each cycle potentially lasting billions or even trillions of years. But what's truly intriguing is how these cycles might allow for interactions between universes. During the collapse phase, as one universe contracts, it could come into contact with another universe that's also collapsing or expanding. These interactions could leave behind traces, such as gravitational waves or patterns in the cosmic microwave background that we might one day detect. The idea of eternal recurrence also raises profound questions about the nature of time and existence. If the universe is cyclical, does that mean every event, every star, and every life form will repeat itself in exactly the same way in future cycles? Or could each cycle bring new variations, creating a multiverse of possibilities? Some theories suggest that the physical laws might change slightly from one cycle to the next, leading to universes with different properties and potentially different forms of life. This cyclic model not only offers a way to explain the origins of our universe, but also provides a framework for understanding how universes in the multiverse might interact. If universes collide or overlap during their cycles, it's possible that energy, matter, or even information could be exchanged between them. These interactions could shape the evolution of each universe, influencing everything from the formation of galaxies to the emergence of life. As we continue, we'll explore how this idea connects to other theories of multiverse interactions and what it might mean for our understanding of reality itself. Now turning to the seventh theory, let's dive into the intriguing idea that black holes could serve as gateways to other universes. Black holes, those mysterious regions of space-time where gravity is so intense that nothing, not even light, can escape, have long fascinated scientists and theorists alike. But what if these cosmic phenomena are more than just destructive forces? What if they are portals to entirely different universes? The concept hinges on the extreme conditions found at the center of a black hole, where the laws of physics as we know them break down. According to some theories, the singularity at the heart of a black hole, a point of infinite density, could be a bridge to another universe. This idea is rooted in the mathematics of general relativity, which suggests that the intense gravitational pull of a black hole could warp space-time so dramatically that it creates a connection, or wormhole, to another region of the multiverse. One of the most compelling aspects of this theory is how it aligns with the idea of multiverse interactions. If black holes are indeed gateways, they could allow for the transfer of matter, energy, or even information between universes. Imagine a scenario where a black hole in our universe connects to a white hole in another, a hypothetical region where matter and energy are expelled rather than absorbed. This could create a cosmic pipeline, enabling interactions that shape the evolution of both universes. But how might we detect such interactions? Some scientists propose that the remnants of these connections could leave observable traces, such as unusual patterns in the cosmic microwave background or anomalies in the behavior of black holes themselves. For instance, if a black hole were to interact with another universe, it might emit gravitational waves with unique signatures that we could one day detect with advanced instruments. The idea of black hole universes also raises profound questions about the nature of reality. If black holes are gateways, does that mean every black hole leads to a different universe? Could these universes have entirely different physical laws, or would they be variations of our own? And if so, what would that mean for the possibility of life in those universes? As we continue to explore the mysteries of black holes and their potential role in multiverse interactions, one thing is clear: these cosmic enigmas hold the key to unlocking some of the deepest questions about the nature of existence. Next, we'll examine how the simulation hypothesis adds another layer to our understanding of multiverse interactions and what it might reveal about the fabric of reality itself. Now turning to the eighth theory, let's explore the simulation hypothesis, a fascinating idea that suggests our universe might be nothing more than an incredibly advanced computer simulation. This theory, popularized by philosophers and scientists alike, raises profound questions about the nature of reality and our place within it. If our universe is a simulation, what does that mean for the existence of other universes, and could there be interactions between them? The simulation hypothesis is rooted in the idea that future civilizations might develop the technology to create simulations so realistic that the beings within them would perceive their world as entirely real. If this is the case, it's possible that our universe is one of countless simulations running on some unimaginably powerful computer. This leads to the intriguing possibility that other simulated universes could exist alongside ours, each with its own set of physical laws and realities. But how might these simulated universes interact? One possibility is that the creators of the simulation, often referred to as programmers or simulators, could design pathways or interfaces between different simulations. These pathways could allow for the transfer of information, energy, or even consciousness between universes. Imagine a scenario where a glitch or intentional modification in one simulation creates a ripple effect that influences another. This could explain phenomena in our universe that seem to defy conventional explanations, such as quantum entanglement or unexplained cosmic anomalies. Another angle to consider is the idea of nested simulations. If our universe is a simulation, it's possible that the beings within it could create their own simulations, leading to layers upon layers of simulated realities. In such a scenario, interactions between these layers could occur, with higher-level simulations influencing those below them. This raises questions about the hierarchy of simulations and whether there's an ultimate base reality that serves as the foundation for all others. The simulation hypothesis also challenges our understanding of free will and determinism. If our universe is a simulation, are our actions and decisions predetermined by the code, or do we have genuine autonomy? And if interactions between simulated universes are possible, could they be used to manipulate outcomes across different realities? While the simulation hypothesis remains speculative, it offers a unique lens through which to view multiverse interactions. It suggests that the boundaries between universes might not be as rigid as we think, and that the fabric of reality could be far more malleable than we've ever imagined. As we continue to ponder the implications of this theory, we're left with more questions than answers, but perhaps that's the point. Next, we'll dive into the concept of quantum foam and how it might explain the bubbling existence of universes within the multiverse. Now turning to the ninth theory, let's explore the multiverse as a quantum foam, a concept that paints a vivid picture of universes bubbling in and out of existence like froth on the surface of an ocean. This idea stems from the strange and unpredictable nature of quantum mechanics, where particles can pop into and out of existence in what scientists call the quantum vacuum. At the smallest scales of space and time, the fabric of reality is thought to be a seething, chaotic foam, constantly churning with energy. In this quantum foam, tiny universes could form spontaneously, existing for fleeting moments before collapsing back into the void. Some of these universes might stabilize, growing into full-fledged realities with their own unique physical laws. This raises the intriguing possibility that our universe is just one of countless bubbles in this cosmic foam, each one a separate, self-contained reality. But how might these bubble universes interact with one another? One possibility is that these bubbles could collide or merge, creating ripples in the fabric of space-time that could be detected as cosmic anomalies. Imagine two bubble universes brushing against each other, their boundaries briefly overlapping. Such an event could transfer energy or matter between the universes, potentially leaving behind observable traces in the form of gravitational waves or unusual patterns in the cosmic microwave background radiation. These interactions might even explain some of the mysterious phenomena we observe in our own universe, such as dark energy or the uneven distribution of matter. Another fascinating aspect of the quantum foam model is the idea that these bubble universes could exist at different scales. Some might be microscopic, lasting only for an instant, while others could expand to become vast, complex realities like our own. This raises the question of whether our universe could be nested within a larger bubble, or if it contains smaller bubbles within it. If so, interactions between these nested universes could occur, with effects cascading up or down through the layers of reality. The quantum foam concept also challenges our understanding of time and causality. In this chaotic, ever-changing environment, the traditional flow of time might break down, allowing for interactions between universes that exist in different temporal states. This could open the door to phenomena like time loops or retrocausality, where events in one universe influence the past or future of another. While the idea of a quantum foam multiverse remains speculative, it offers a compelling framework for thinking about how universes might interact on the smallest scales. It suggests that the boundaries between realities are not fixed but fluid, constantly shifting and reshaping in the cosmic froth. As we continue to explore this theory, we're left to wonder what other secrets the quantum foam might hold, and whether we'll ever find evidence of these fleeting bubble universes. Next, we'll delve into the string theory landscape and how it envisions a multiverse filled with diverse, interconnected realities. Now turning to the 10th theory, let's dive into the concept of the landscape multiverse, a fascinating idea rooted in string theory. String theory suggests that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings can vibrate in countless ways, each corresponding to different particles and forces. But what makes this theory truly mind-bending is the idea that these vibrations could give rise to an almost infinite variety of universes, each with its own unique set of physical laws and constants. In the landscape multiverse, these universes are thought to exist within a vast, multidimensional space known as the string theory landscape. Imagine this landscape as a cosmic terrain filled with valleys, hills, and plateaus, where each point represents a different universe with its own distinct properties. Some universes might have stronger gravity, while others could have weaker electromagnetic forces. Some might even have extra dimensions of space that are curled up so tightly we can't perceive them. But how do these universes interact or influence one another? One possibility is that they are connected through higher dimensional membranes or branes, which are central to string theory. These branes could act as bridges between universes, allowing energy, matter, or even information to flow between them. For example, if two branes collide or overlap, it could create a burst of energy that ripples through both universes, potentially leaving behind observable effects like gravitational waves or unusual cosmic structures. Another intriguing aspect of the landscape multiverse is the idea of tunneling between universes. In quantum mechanics, particles can sometimes tunnel through barriers that would normally be impossible to cross. Similarly, universes in the string theory landscape might occasionally tunnel into one another, leading to sudden changes in their physical properties. This could explain phenomena like the sudden appearance of dark energy or the mysterious fine-tuning of our universe's constants. The landscape multiverse also raises questions about the nature of reality itself. If there are countless universes with different physical laws, why does ours have the specific constants that allow for the existence of stars, planets, and life? Some scientists suggest that this is a result of the Anthropic Principle. Our universe is the way it is because it's one of the rare ones capable of supporting life. But others propose that interactions between universes might play a role, with more stable or fit universes influencing their neighbors over time. While the landscape multiverse remains a theoretical framework, it offers a rich and imaginative way to think about the diversity of possible realities. It challenges us to consider how the laws of physics might vary across the cosmos and how these variations could lead to interactions between universes. As we continue to explore this idea, we're left to wonder what other surprises the string theory landscape might hold, and whether we'll ever find evidence of these otherworldly connections. Next, we'll examine the mathematical universe hypothesis and how it envisions a multiverse built entirely on mathematical structures. Now turning to the 11th theory, let's explore the mathematical universe hypothesis, a bold and intriguing idea proposed by physicist Max Tegmark. This hypothesis suggests that every possible mathematical structure exists as a physical universe. In other words, if something can be described mathematically, it exists somewhere in the multiverse. This means that universes aren't just governed by mathematical laws, they are mathematical structures themselves. Imagine the multiverse as an infinite library, where each book represents a unique mathematical structure. Some books might describe universes with 3 dimensions of space and 1 of time, like ours, while others could depict realities with entirely different geometries or even extra dimensions. The mathematical universe hypothesis doesn't just stop at the familiar laws of physics. It encompasses every conceivable mathematical possibility, no matter how strange or abstract. But how could these mathematical universes interact? One possibility is through shared mathematical frameworks. For example, 2 universes might overlap or intersect in a higher dimensional space, allowing their structures to influence one another. This could lead to phenomena like quantum entanglement, where particles in separate universes remain connected despite vast distances. Another idea is that universes could communicate through mathematical symmetries or patterns, creating echoes or resonances that ripple across the multiverse. The mathematical universe hypothesis also raises profound questions about the nature of reality. If all mathematical structures exist, why do we perceive the universe we do? Tegmark suggests that our universe might simply be one of the structures that allows for conscious observers like us. In other words, we experience this particular universe because its mathematical properties make life and consciousness possible. This ties back to the Anthropic Principle, which we've touched on earlier, but with a mathematical twist. What's truly fascinating is that this hypothesis blurs the line between mathematics and physics. It suggests that the universe isn't just described by math, it is math. This opens up the possibility that interactions between universes could be governed by mathematical relationships, such as equations or symmetries, rather than physical forces like gravity or electromagnetism. It's a radical rethinking of what the multiverse could be and how it might operate. While the mathematical universe hypothesis is still speculative, it challenges us to think about reality in a fundamentally new way. It invites us to consider whether the universe is a mathematical object and whether other mathematical realities might exist alongside ours. As we continue to explore this idea, we're left to wonder, could the multiverse itself be a vast, interconnected web of mathematical structures, each one a universe waiting to be discovered? Next, we'll delve into the Anthropic Principle and how it ties into the fine-tuning of our universe. Now turning to the 12th theory, let's explore the Anthropic Principle and its connection to the fine-tuning of our universe. The Anthropic Principle is the idea that the conditions we observe in our universe must be compatible with the existence of conscious life, because if they weren't, we wouldn't be here to observe them. This principle often raises a profound question. Why does our universe seem so perfectly fine-tuned for life? The answer, some suggest, lies in the existence of a multiverse. Imagine a vast array of universes, each with its own set of physical constants and laws. In some universes, the strength of gravity might be too weak to form stars, while in others, the fundamental forces might be so strong that atoms could never stabilize. Among this infinite variety, only a tiny fraction of universes would have the precise conditions needed to support life. Our universe, with its finely tuned constants, is one of those rare exceptions. The Anthropic Principle suggests that we observe these specific conditions not because they're special in any cosmic sense, but because they're the only conditions under which life, and therefore observers like us, could exist. But how does this relate to multiverse interactions? If multiple universes exist, each with different physical laws, it's possible that some of these universes could influence one another. For example, universes with similar or overlapping physical constants might interact through shared quantum fields or higher dimensional spaces. These interactions could manifest as subtle anomalies in our own universe, such as unexplained fluctuations in cosmic background radiation or peculiar patterns in particle behavior. Some scientists even speculate that fine-tuning itself could be the result of interactions between universes, with our universe inheriting its life-friendly properties from a neighboring one. Another intriguing possibility is that universes could collide or merge, creating regions where the laws of physics temporarily blend. These collisions might leave behind observable signatures, such as irregularities in the distribution of galaxies or unexpected variations in the cosmic microwave background. While such events would be rare, they could provide evidence for the existence of other universes and their potential interactions with ours. The Anthropic Principle also ties back to earlier theories we've discussed, such as the mathematical universe hypothesis. If every possible mathematical structure exists as a universe, then the fine-tuning of our universe might simply reflect the fact that we inhabit one of the structures capable of supporting life. This perspective shifts the focus from "why is our universe special?" to "what makes our universe possible?" It's a subtle but profound shift that invites us to consider the multiverse not as a collection of random possibilities, but as a vast, interconnected system where life-friendly universes are rare but inevitable. As we ponder the implications of the Anthropic Principle, we're left with a fascinating question. Could the fine-tuning of our universe be evidence of a deeper, multiverse-level order? And if so, what might that mean for our understanding of reality? Next, we'll explore the Ekpyrotic universe model, which offers yet another perspective on how universes might interact in the cosmic dance of existence. Now turning to the 13th theory, let's dive into the Ekpyrotic universe model, a fascinating idea that reimagines the birth and interaction of universes. Unlike the traditional Big Bang theory, which suggests our universe began from a single, infinitely dense point, the Ekpyrotic model proposes that our universe is the result of a collision between two higher-dimensional branes in a larger, multidimensional space. These branes, short for membranes, are like vast sheets of energy and matter that exist in dimensions beyond the three spatial dimensions we experience. Imagine two enormous sheets floating in a higher dimensional void, slowly moving toward each other. When they collide, the energy released from the impact creates the conditions for a new universe to form. This collision isn't a one-time event. It's part of a cyclical process where universes collide, expand, cool, and eventually drift apart, only to collide again in an endless cosmic dance. This model offers a compelling alternative to the Big Bang, suggesting that the universe we inhabit is just one episode in an infinite series of cosmic cycles. But how does this relate to multiverse interactions? If multiple branes exist in this higher dimensional space, each collision could give rise to a new universe with its own unique properties. These universes might interact indirectly through the shared higher dimensional space, influencing each other's evolution. For example, the energy from one collision could ripple through the higher dimensional void and affect the timing or intensity of another collision, creating a network of interconnected universes. One of the most intriguing aspects of the Ekpyrotic model is the possibility of observable evidence. If our universe was born from a brane collision, the event might have left behind subtle traces in the cosmic microwave background, the faint afterglow of the Big Bang. Scientists have speculated that certain irregularities or patterns in this background radiation could be signatures of such a collision. Additionally, the model predicts that gravitational waves, ripples in spacetime, could carry information about these higher dimensional interactions, offering a potential window into the multiverse. The Ekpyrotic model also ties into earlier theories we've explored, such as the cyclic universe and brane collisions in string theory. It suggests that the multiverse isn't just a collection of isolated universes, but a dynamic, interconnected system where universes are constantly being born, evolving, and interacting. This perspective challenges us to think of the multiverse not as a static backdrop, but as a living, breathing entity with its own rhythms and cycles. As we reflect on the Ekpyrotic model, we're left with a profound question. Could the universe we see around us be just one chapter in an infinite cosmic story? And if so, what might the next chapter hold? Next, we'll explore the idea of the multiverse as a quantum computer, where universes themselves might function as qubits in a vast computational system. Now turning to the 14th theory, let's explore the idea of the multiverse as a quantum computer. This concept takes inspiration from the principles of quantum computing, where information is processed using quantum bits or qubits, which can exist in multiple states simultaneously. In this model, each universe within the multiverse could be thought of as a qubit, capable of interacting with other universes in ways that defy our classical understanding of reality. Imagine the multiverse as a vast, interconnected quantum computer, where each universe represents a unique piece of information. Just as qubits in a quantum computer can be entangled, sharing information instantaneously across vast distances, universes in this multiverse could be similarly linked. This entanglement could allow for interactions between universes, where changes in one universe ripple through the quantum fabric and influence others. For example, a quantum event in one universe might trigger a corresponding event in another, creating a network of cause and effect that spans the multiverse. One of the most fascinating implications of this theory is the idea that the multiverse could be performing computations on a cosmic scale. If universes are qubits, then the interactions between them could be part of a grand computational process, solving problems or generating outcomes that are beyond the reach of any single universe. This raises the possibility that the multiverse itself could be a kind of cosmic intelligence, processing information and evolving in ways we can barely comprehend. But how might we detect evidence of such a system? If the multiverse operates like a quantum computer, it could leave behind subtle signatures in the structure of our own universe. For instance, certain patterns in the distribution of galaxies or the behavior of particles at the quantum level might hint at the underlying computational processes. Additionally, the concept of quantum entanglement between universes could provide a mechanism for faster-than-light communication, offering a potential explanation for phenomena that currently defy our understanding of physics. This theory also ties into earlier ideas we've explored, such as the holographic principle and the simulation hypothesis. If the multiverse is a quantum computer, it could be seen as a higher dimensional system projecting our reality, much like a hologram. Alternatively, it could suggest that our universe is part of a vast simulation, with each universe acting as a node in a cosmic computational network. As we consider the multiverse as a quantum computer, we're left with a profound question. Could the interactions between universes be part of a larger, purposeful process? And if so, what might the ultimate goal of this cosmic computation be? Next, we'll delve into the concept of the multiverse as a fractal, where universes are nested within each other in an infinite, self-similar pattern. Now turning to the 15th theory, let's explore the idea of the multiverse as a fractal. This concept draws inspiration from the mathematical beauty of fractals, where patterns repeat themselves at every scale, creating infinite complexity within a finite space. In this model, universes are not just separate entities but are nested within each other, forming an intricate, self-similar structure that spans across dimensions. Imagine a universe within a universe, like a Russian nesting doll, where each layer contains its own unique set of physical laws and realities. In this fractal multiverse, the boundaries between universes are not rigid but fluid, allowing for interactions that transcend the limits of space and time. For example, a phenomenon in one universe could ripple through the fractal structure, influencing neighboring universes in ways that are both subtle and profound. One of the most intriguing aspects of this theory is the idea that the fractal nature of the multiverse could explain the fine-tuning of our own universe. If universes are nested within each other, the conditions in one universe could be influenced by the properties of the larger universe it resides in. This could create a cascade of interactions where the laws of physics in one universe are shaped by the overarching structure of the fractal multiverse. But how might we detect evidence of such a fractal multiverse? One possibility lies in the patterns we observe in the cosmos. If the multiverse is fractal, we might expect to see repeating structures or symmetries in the distribution of galaxies, cosmic microwave background radiation, or even the behavior of particles at the quantum level. These patterns could serve as clues, hinting at the underlying fractal geometry of the multiverse. This theory also connects to earlier ideas we've discussed, such as the holographic principle and the landscape multiverse. If the multiverse is fractal, it could suggest that our universe is a projection of a higher dimensional reality, much like a hologram. Alternatively, it could imply that the multiverse is a vast, interconnected network of universes, each with its own unique set of physical constants, yet all part of a larger, self-similar pattern. As we ponder the fractal multiverse, we're left with a fascinating question. Could the interactions between nested universes be part of a grand cosmic design? And if so, what might this design reveal about the nature of reality itself? Next, we'll examine the role of dark energy in the multiverse and how varying levels of this mysterious force could lead to interactions between universes. Now turning to the 16th theory, let's delve into the role of dark energy in the multiverse. Dark energy, the mysterious force driving the accelerated expansion of our universe, might play a crucial role in shaping the interactions between universes. In a multiverse scenario, each universe could have its own unique amount of dark energy, leading to vastly different rates of expansion and contraction. This variation could create opportunities for universes to interact in unexpected ways. Imagine a universe with a high concentration of dark energy, expanding rapidly and stretching its boundaries. Nearby, another universe with less dark energy might be expanding more slowly or even contracting. The tension between these differing rates of expansion could create regions where the fabric of space-time overlaps or collides, allowing for interactions between the two universes. These interactions might manifest as gravitational waves, cosmic radiation, or even the exchange of particles across the boundary. One intriguing possibility is that dark energy could act as a bridge between universes. In regions where dark energy levels are similar, universes might temporarily align, creating pathways for energy or information to flow between them. This could explain phenomena like quantum entanglement, where particles in separate universes might remain connected despite vast distances. Alternatively, dark energy could influence the formation of cosmic structures, such as galaxies or galaxy clusters, in ways that hint at the presence of neighboring universes. The implications of dark energy in the multiverse are profound. If dark energy levels vary significantly across universes, it could mean that some universes are destined to expand forever, while others might collapse or cycle through periods of expansion and contraction. These differences could lead to a dynamic multiverse, where universes interact, merge, or even give birth to new universes over time. As we explore the role of dark energy, we're left with a compelling question. Could the interactions between universes be driven by the ebb and flow of this enigmatic force? And if so, what might this tell us about the ultimate fate of our own universe? Next, we'll explore the idea that time travel could enable interactions between universes, opening up new possibilities for understanding the multiverse. Now turning to the 17th theory, let's explore the fascinating idea that time travel could enable interactions between universes. Time travel has long been a staple of science fiction, but could it also be a key to understanding the multiverse? According to some theories, the ability to move through time might not just be limited to our own universe, but could extend across the boundaries of parallel realities. Imagine a scenario where a time traveler from our universe ventures into the past or future, only to find themselves in a different universe altogether. This could happen if each decision or event creates a branching timeline, as suggested by the many worlds interpretation. In this framework, time travel might not just alter the past of our universe, but could also open doorways to entirely new realities. For instance, a traveler who changes a significant event in the past might not return to their original timeline, but instead find themselves in a parallel universe where that event unfolded differently. However, time travel within the multiverse raises some intriguing paradoxes. The classic grandfather paradox, where a time traveler prevents their own existence, becomes even more complex when multiple universes are involved. If a traveler alters an event in a parallel universe, does it affect their original timeline, or does it simply create a new branch? Some theories suggest that time travel could act as a bridge between universes, allowing information or even matter to flow between them. This could explain phenomena like déjà vu or precognitive dreams, where individuals might be tapping into experiences from alternate timelines. Another possibility is that time travel could enable civilizations from different universes to communicate or collaborate. Advanced beings might use time travel to send messages across universes, creating a network of interconnected realities. This could lead to a form of multiverse diplomacy, where knowledge and resources are shared between universes to solve common challenges or explore new frontiers. Of course, the idea of time travel enabling multiverse interactions is still highly speculative. The physics of time travel remains one of the most debated topics in science, and the mechanisms by which it could connect universes are far from understood. Yet the possibilities are tantalizing. Could time travel be the key to unlocking the secrets of the multiverse? And if so, what might we discover about our place in the grand tapestry of reality? Next, we'll delve into the intriguing connection between consciousness and the multiverse, exploring how our minds might interact with other universes. Now turning to the 18th theory, let's explore the intriguing connection between consciousness and the multiverse. Could our minds be more than just products of our own universe? Some theories suggest that consciousness itself might be a bridge to other realities, allowing us to interact with or even perceive alternate universes. One idea is that consciousness operates on a level that transcends the physical boundaries of our universe. In this view, the mind isn't confined to the brain but exists as a kind of quantum phenomenon capable of tapping into the multiverse. This could explain experiences like intuition, déjà vu, or even dreams where we might be glimpsing fragments of other realities. For instance, have you ever had a dream that felt so vivid and real, as if you were living in another world? Some theorists propose that these experiences could be moments when our consciousness briefly connects with a parallel universe. Another fascinating concept is that consciousness might act as a kind of filter, allowing us to perceive only one universe at a time while countless others exist simultaneously. This idea aligns with the many worlds interpretation, where every possible outcome of a decision creates a new universe. In this framework, our consciousness could be like a radio tuner, selecting one frequency our current reality, while other frequencies or universes remain just out of reach. But what if we could adjust that tuner? Could advanced meditation, altered states of consciousness, or even technology allow us to access other realities? Some researchers have even speculated that consciousness could be a fundamental feature of the multiverse itself. In this view, every universe might have its own form of consciousness, and interactions between universes could occur through a kind of shared mental field. This could open up possibilities for communication or even collaboration between conscious beings across different realities. Imagine a future where we could exchange ideas or knowledge with civilizations in other universes, all through the power of consciousness. Of course, these ideas are still highly speculative, and the science of consciousness remains one of the most mysterious areas of study. Yet, the notion that our minds might interact with the multiverse is both thrilling and thought-provoking. Could consciousness be the key to unlocking the secrets of parallel realities? And if so, what might we discover about the nature of existence itself? Next, we'll examine how quantum entanglement might provide evidence of interactions between universes, offering another piece of the multiverse puzzle. Now turning to the 19th theory, let's dive into the fascinating connection between quantum entanglement and the multiverse. Quantum entanglement is one of the most puzzling phenomena in physics, where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. But what if this strange connection isn't just happening within our universe? Could it be evidence of interactions between parallel realities? Some scientists have proposed that entangled particles might actually be linked across different universes. In this view, when two particles become entangled, they're not just connected through space, they're connected through the fabric of the multiverse itself. This could mean that the seemingly instantaneous communication between entangled particles isn't breaking the rules of our universe, but is instead a sign of a deeper connection between universes. Imagine two particles in separate realities, still influencing each other as if they were right next door. This idea challenges our understanding of space, time, and the very nature of reality. If quantum entanglement does involve interactions between universes, it could have profound implications. For one, it might explain why entanglement seems to defy the speed of light. If the connection between particles isn't limited to our universe, then the rules of our reality wouldn't apply. This could also mean that the multiverse isn't just a collection of isolated bubbles, but a deeply interconnected web, where universes constantly influence each other in ways we're only beginning to understand. Another intriguing possibility is that entanglement could serve as a kind of bridge between universes. If we could harness or manipulate entangled particles, might we find a way to send information, or even ourselves, across the multiverse? While this sounds like science fiction, some researchers believe that advanced civilizations in other universes might already be using entanglement as a form of communication. Could we one day tap into this cosmic network and exchange knowledge with beings from alternate realities? Of course, these ideas are still in the realm of theory, and much remains to be discovered. But the idea that quantum entanglement could be a window into the multiverse is both exciting and mind-bending. It challenges us to rethink not only the nature of particles, but also the very structure of existence. As we continue to explore the mysteries of quantum mechanics, could entanglement be the key to unlocking the secrets of the multiverse? Next, we'll explore the idea of parallel timelines and how they might interact within the vast tapestry of the multiverse. Now turning to the 20th theory, let's explore the captivating concept of parallel timelines within the multiverse. Imagine a vast tapestry of realities, each one branching off from the decisions we make, the events that unfold, and the countless possibilities that exist at every moment. These parallel timelines suggest that every choice, no matter how small, could create a new universe where history takes a different path. But what happens when these timelines interact or even merge? Could we find evidence of such interactions in our own universe? One intriguing idea is that parallel timelines might occasionally overlap or collide, creating moments where the boundaries between realities blur. Think of it like two rivers merging into one. What was once separate becomes intertwined. In the multiverse, this could mean that events from one timeline might influence another, or that fragments of alternate histories could seep into our own. Some scientists speculate that certain anomalies or unexplained phenomena in our universe might be the result of such interactions. For example, déjà vu or strange coincidences could be glimpses of overlapping timelines where fragments of another reality briefly touch our own. Another possibility is that parallel timelines could merge entirely, creating a new, unified reality. This could happen if two timelines become so similar that they essentially collapse into one. Imagine two versions of history that are nearly identical, differing only in the smallest details. Over time, these differences might fade, and the timelines could merge into a single, cohesive universe. This idea raises fascinating questions about the nature of time and reality. Could the universe itself be constantly reshaping, with timelines merging and diverging like threads in a cosmic tapestry? The concept of parallel timelines also opens the door to the idea of time travel. If multiple timelines exist, could we find a way to move between them? Some theories suggest that advanced civilizations might have the technology to navigate these timelines, visiting alternate versions of history or even altering the course of events. While this remains speculative, it's a thrilling thought experiment that challenges our understanding of cause and effect. As we ponder the possibilities of parallel timelines, it's clear that the multiverse is far more complex than we once imagined. It's not just a collection of isolated universes, but a dynamic, interconnected web of realities, each one shaped by the choices and events of countless timelines. The idea that these timelines could interact or merge adds another layer of mystery to the multiverse, inviting us to rethink our place in the grand scheme of existence. Next, we'll delve into the role of cosmic strings and how they might connect universes in ways we're only beginning to understand. Now turning to the 21st theory, let's explore the fascinating concept of cosmic strings and their potential role in connecting universes within the multiverse. Cosmic strings are hypothetical, one-dimensional structures that could have formed in the early universe, remnants of the intense energy fluctuations that occurred just moments after the Big Bang. These strings are thought to be incredibly thin but unimaginably dense, stretching across vast distances of space. But what makes them truly intriguing is the possibility that they could act as bridges between different universes, creating pathways for interactions that defy our current understanding of physics. Imagine cosmic strings as threads woven through the fabric of space-time, connecting distant regions of the multiverse like a cosmic web. These strings could serve as conduits for energy, matter, or even information to travel between universes. Some theories suggest that if two universes are connected by a cosmic string, particles or forces from one universe could influence the other, creating observable effects that might hint at the existence of the multiverse. For example, unusual gravitational waves or unexplained energy signatures in our universe could be evidence of such interactions. Another intriguing idea is that cosmic strings might not just connect universes but also influence their evolution. As these strings vibrate or move through space-time, they could create ripples that affect the structure and behavior of the universes they connect. This could lead to phenomena like the formation of galaxies, the distribution of dark matter, or even the acceleration of cosmic expansion. In this way, cosmic strings might play a crucial role in shaping the multiverse, acting as both connectors and catalysts for change. The concept of cosmic strings also raises questions about the nature of spacetime itself. If these strings exist, they could reveal new insights into the fundamental forces that govern the universe, such as gravity and quantum mechanics. Some scientists speculate that studying cosmic strings could help us bridge the gap between these two seemingly incompatible frameworks, bringing us closer to a unified theory of everything. As we consider the potential of cosmic strings to connect and influence universes, it's clear that they add another layer of complexity to the multiverse. These mysterious structures challenge us to think beyond the boundaries of our own universe and imagine a cosmos where everything is interconnected. Next, we'll explore the idea of wormholes and how they might serve as even more direct pathways between universes, opening up possibilities for travel and interaction that stretch the limits of our imagination. Now turning to the 22nd theory, let's delve into the captivating idea of wormholes and their potential to serve as bridges between universes. Wormholes, often depicted in science fiction as shortcuts through space and time, are theoretical passages that could connect distant regions of the universe or even entirely different universes. These cosmic tunnels are rooted in the equations of general relativity, which describe how massive objects warp the fabric of spacetime. A wormhole, in essence, is a shortcut through this warped spacetime, potentially allowing for rapid travel between two points that would otherwise be impossibly far apart. The concept of wormholes hinges on the idea of spacetime curvature. Imagine folding a piece of paper so that two distant points touch. A wormhole would be like poking a hole through the folded paper, creating a direct path between those points. In the context of the multiverse, wormholes could theoretically connect not just different regions of our universe, but entirely separate universes. This raises the tantalizing possibility of multiverse travel, where beings or information could traverse these tunnels to explore or interact with other realities. However, the physics of wormholes is far from straightforward. For a wormhole to be stable and traversable, it would require exotic matter with negative energy density to keep it open. This exotic matter would counteract the natural tendency of the wormhole to collapse under its own gravity. While such matter has not been observed in nature, its existence is not ruled out by the laws of physics, leaving the door open for speculation and exploration. One of the most intriguing aspects of wormholes is their potential to enable interactions between universes. If a wormhole connected two universes, particles, energy, or even information could theoretically pass through, creating observable effects in both realities. For example, a burst of energy or a strange gravitational anomaly in our universe could be evidence of such a connection. This idea aligns with some theories suggesting that wormholes could be the key to understanding phenomena like dark energy or the accelerating expansion of the universe. Wormholes also raise profound questions about causality and the nature of time. If a wormhole allowed for faster-than-light travel, it could potentially enable time travel, leading to paradoxes and challenges to our understanding of cause and effect. These complexities make wormholes not just a fascinating theoretical concept, but also a rich area for scientific inquiry, pushing the boundaries of our knowledge about the universe and the multiverse. As we ponder the possibilities of wormholes as bridges between universes, it's clear that they represent one of the most exciting and speculative ideas in modern physics. They challenge us to rethink the nature of space-time, causality, and the very fabric of reality. Next, we'll explore how quantum tunneling could allow particles to move between universes, opening up yet another avenue for multiverse interactions. Now turning to the 23rd theory, let's explore the fascinating concept of quantum tunneling and its potential role in enabling interactions between universes. Quantum tunneling is a phenomenon in which particles pass through barriers that, according to classical physics, should be impossible to overcome. This strange behavior arises from the probabilistic nature of quantum mechanics, where particles exist in a state of uncertainty until they are observed. In essence, a particle can tunnel through a barrier even if it doesn't have enough energy to surmount it, defying our everyday intuition. In the context of the multiverse, quantum tunneling could provide a mechanism for particles to move between universes. Imagine a particle existing in one universe encountering a barrier, a kind of cosmic wall separating it from another universe. Through quantum tunneling, that particle could, in theory, pass through this barrier and emerge in a neighboring universe. This process wouldn't require the particle to travel through the space between universes in the traditional sense. Instead, it would simply appear on the other side, as if it had bypassed the barrier entirely. The implications of this are profound. If particles can tunnel between universes, it raises the possibility of subtle interactions or exchanges of energy and information across the multiverse. For example, a particle tunneling from one universe to another could carry with it a small amount of energy, potentially leaving a detectable signature in both realities. This could explain certain anomalies in our universe, such as unexplained energy fluctuations or mysterious particles that seem to appear out of nowhere. Quantum tunneling also challenges our understanding of the boundaries between universes. If particles can move between them, it suggests that these boundaries are not as rigid or impenetrable as we might assume. Instead, they could be porous, allowing for a kind of quantum leakage between realities. This idea aligns with some theories proposing that the multiverse is not a collection of entirely isolated universes, but rather a network of interconnected realms, with quantum tunneling serving as one of the bridges between them. However, the practical implications of quantum tunneling for multiverse interactions remain speculative. While the phenomenon is well documented at the quantum scale, such as in the behavior of electrons in atoms, it's unclear whether it could operate on the much larger scales required to connect entire universes. Additionally, the energy required for such tunneling events might be prohibitively high, making them rare or even impossible under normal conditions. Still, the idea opens up exciting possibilities for further exploration and theoretical modeling. As we consider the role of quantum tunneling in the multiverse, it's clear that this phenomenon adds another layer of complexity to our understanding of reality. It challenges us to think beyond the limits of classical physics and imagine a cosmos where the boundaries between universes are not fixed but fluid, shaped by the strange and unpredictable rules of quantum mechanics. Next, we'll delve into the Big Bounce theory, exploring how the cyclical expansion and contraction of universes could lead to interactions across the multiverse. Now turning to the 24th theory, let's explore the Big Bounce theory and its implications for multiverse interactions. The Big Bounce theory proposes that our universe is not the result of a single Big Bang, but part of an endless cycle of expansion and contraction. According to this idea, when a universe reaches the end of its expansion phase, it begins to collapse under the force of gravity. Instead of collapsing into a singularity, however, it rebounds in a new Big Bang, giving birth to a new universe. This cycle of expansion, contraction, and rebirth could repeat indefinitely, creating a multiverse of interconnected universes. In this cyclical model, interactions between universes could occur during the moments of transition when one universe collapses and another begins to expand. Imagine two universes existing side by side, each at a different stage in its cycle. As one universe contracts, its energy and matter could spill over into the neighboring universe, creating a kind of cosmic exchange. This transfer of energy and information could lead to observable effects, such as unusual patterns in the cosmic microwave background or anomalies in the distribution of galaxies. The Big Bounce theory also raises intriguing questions about the nature of time and causality. If universes are reborn in an endless cycle, does time flow in a straight line, or is it cyclical as well? Could events in one universe influence the development of another, creating a web of cause and effect that spans the multiverse? These questions challenge our understanding of reality and suggest that the boundaries between universes might be more fluid than we once thought. However, the Big Bounce theory is not without its challenges. One major hurdle is explaining how a collapsing universe could rebound without collapsing into a singularity, a point of infinite density where the laws of physics break down. Some theories propose that quantum effects could prevent this collapse, allowing the universe to bounce back instead. Others suggest that higher dimensional physics or modifications to general relativity might be necessary to explain the mechanism behind the bounce. Despite these uncertainties, the Big Bounce theory offers a compelling vision of a multiverse where universes are not isolated but connected through cycles of birth, death, and rebirth. It invites us to consider the possibility that our universe is just one chapter in an infinite cosmic story, with each cycle bringing new opportunities for interaction and exchange. As we move forward, we'll explore the final theory in our list, the holographic multiverse, and how it envisions the multiverse as a projection of a higher dimensional reality. Now turning to the 25th and final theory in our exploration of multiverse interactions, let's delve into the concept of the holographic multiverse. This theory suggests that our universe, and potentially all universes within the multiverse, could be holographic projections of a higher dimensional reality. Imagine a hologram where a three-dimensional image is encoded on a two-dimensional surface. In the same way, the holographic multiverse proposes that everything we perceive as reality, space, time, matter, and energy, might be a projection from a higher dimensional surface or boundary. This idea stems from the holographic principle, which originated in the study of black holes. Scientists discovered that all the information about objects falling into a black hole could be encoded on its event horizon, the boundary surrounding the black hole. Extending this principle to the multiverse, the holographic multiverse theory suggests that each universe could be a holographic projection from a higher dimensional space. In this framework, interactions between universes might occur through the higher dimensional source that encodes them. Just as two holograms projected from the same surface could influence each other, universes in the holographic multiverse might interact through their shared higher dimensional origin. One fascinating implication of this theory is that it could explain phenomena like quantum entanglement, where particles separated by vast distances appear to influence each other instantaneously. If our universe is a hologram, entangled particles might be connected through the higher dimensional reality that encodes them, allowing for interactions that seem to defy the limits of space and time. Similarly, the holographic multiverse could provide a framework for understanding how information or energy might transfer between universes, even if they appear entirely separate in our three-dimensional perspective. The holographic multiverse also challenges our understanding of reality itself. If our universe is a projection, then what we perceive as solid and real might be just a shadow of a deeper, more complex reality. This raises profound questions about the nature of existence and the limits of human perception. Could other universes with different physical laws or dimensions also be projections from the same higher dimensional source? And if so, how might these universes interact or influence one another? While the holographic multiverse theory is still speculative, it offers a bold and imaginative vision of the multiverse. It suggests that the boundaries between universes might not be as rigid as we think, and that interactions could occur in ways that transcend our current understanding of physics. As we conclude our journey through these 25 theories, we're left with a sense of awe at the vast possibilities that the multiverse holds. Each theory invites us to rethink our place in the cosmos and to consider that reality might be far more interconnected and mysterious than we ever imagined. Now turning to the first theory expanded, let's dive deeper into the implications of quantum superposition and how it could lead to observable effects in our universe. Quantum superposition is one of the most fascinating and mind-bending concepts in quantum mechanics. It suggests that particles can exist in multiple states at once until they are observed or measured. Think of it like a coin spinning in the air. It's neither heads nor tails until it lands. In the quantum world, particles can be in a state of both until something forces them to choose. This idea has profound implications for the existence of parallel universes. If particles can exist in multiple states simultaneously, then every possible outcome of a quantum event could give rise to a new universe. For example, imagine a particle that can move left or right. In one universe, it moves left, and in another, it moves right. This branching of possibilities is at the heart of the many worlds interpretation which we touched on earlier. But what's even more intriguing is how this might manifest in our observable universe. One potential effect of quantum superposition is quantum interference. This occurs when particles, like electrons or photons, behave as waves and interfere with themselves, creating patterns that can only be explained if they've traveled multiple paths simultaneously. Experiments like the double-slit experiment have shown this phenomenon in action. When particles pass through two slits, they create an interference pattern on a screen, as if they've traveled through both slits at once. This suggests that, at the quantum level, particles are exploring multiple possibilities simultaneously, hinting at the existence of parallel realities. Another observable effect could be quantum tunneling, where particles pass through barriers that they shouldn't be able to according to classical physics. This phenomenon is crucial in processes like nuclear fusion in stars and even in modern electronics. If particles can tunnel through barriers, it might be because they're interacting with other versions of themselves in parallel universes where the barrier doesn't exist or is weaker. Quantum superposition also raises questions about the nature of reality itself. If particles can exist in multiple states at once, does that mean our universe is just one of countless possibilities? And if so, could we ever detect evidence of these parallel universes? Some scientists speculate that tiny fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang, might hold clues. These fluctuations could be the fingerprints of interactions between our universe and others, left behind in the early moments of the cosmos. While the idea of parallel universes born from quantum superposition is still speculative, it challenges us to rethink the boundaries of reality. It suggests that the universe is far more dynamic and interconnected than we once thought, with every quantum decision potentially creating a new branch of existence. As we continue to explore these ideas, we're reminded that the mysteries of the multiverse are as vast as they are profound, inviting us to question what we know and imagine what might be. Now turning to the many worlds interpretation, let's explore the fascinating debates that surround this theory and why it continues to captivate scientists and philosophers alike. The many worlds interpretation proposed by physicist Hugh Everett in the 1950s suggests that every quantum decision spawns a new universe. In other words, every possible outcome of a quantum event actually happens, but in a separate, branching reality. This idea is both elegant and mind-bending, offering a way to explain the strange behavior of particles without invoking the need for an observer to collapse a quantum state. One of the strengths of the many worlds interpretation is its simplicity. Unlike other interpretations of quantum mechanics, it doesn't require any additional rules or mechanisms to explain why particles behave the way they do. It simply says that all possible outcomes occur, each in its own universe. This makes it a compelling framework for understanding phenomena like quantum superposition and entanglement. For example, when a particle is in a superposition of states, the many worlds interpretation suggests that it's not just in multiple states, it's in multiple universes, each corresponding to one of those states. However, this theory is not without its challenges. One of the biggest criticisms is that it seems untestable. If every possible outcome happens in a separate universe, how could we ever observe or interact with these other realities? Critics argue that this makes the many worlds interpretation more of a philosophical idea than a scientific one. After all, science relies on evidence and observation, and if we can't detect these parallel universes, can we really say they exist? Another point of debate is the sheer scale of the multiverse that the many worlds interpretation implies. If every quantum decision creates a new universe, then the number of universes would be unimaginably vast, far beyond anything we can comprehend. Some scientists find this idea unsettling, as it raises questions about the nature of reality and our place within it. Are we just one of an infinite number of versions of ourselves, each living out a slightly different life in a different universe? And if so, what does that mean for concepts like free will and identity? Despite these challenges, the many worlds interpretation has its defenders. Some argue that it's the most straightforward way to make sense of quantum mechanics, even if it leads to some uncomfortable conclusions. Others point out that while we may not be able to observe other universes directly, there could be indirect evidence. For example, some researchers have proposed that tiny anomalies in the cosmic microwave background radiation or unexplained quantum effects could be hints of interactions between our universe and others. The many worlds interpretation also raises profound philosophical questions. If every possible outcome happens, does that mean everything that can happen does happen? And if so, what does that say about the nature of existence? These questions push us to think beyond the limits of our current understanding and consider the possibility that reality is far more complex and interconnected than we ever imagined. As we continue to explore the many worlds interpretation, we're reminded that science is not just about finding answers, it's about asking the right questions. Whether or not this theory is ultimately proven, it challenges us to rethink our assumptions and imagine a universe that is far stranger and more wonderful than we ever thought possible. Now turning to the concept of bubble universes, let's dive into the intriguing evidence that supports their existence and how scientists might one day detect them. Bubble universes are a fascinating idea that emerges from the theory of cosmic inflation, which suggests that our universe underwent a rapid expansion just moments after the Big Bang. During this period, it's possible that other regions of space-time also expanded, forming separate bubbles that each became their own universe. These bubble universes could exist alongside ours, each with its own unique set of physical laws and constants. One of the key pieces of evidence for bubble universes comes from the cosmic microwave background radiation, or CMB, which is the faint afterglow of the Big Bang. Scientists have been studying the CMB for decades, looking for tiny irregularities that could reveal clues about the early universe. Some researchers believe that if our universe collided with another bubble universe in the distant past, it might have left a distinctive mark in the CMB. These marks could appear as unusual patterns or bruises in the radiation, providing indirect evidence of another universe's existence. Another potential way to detect bubble universes is through gravitational waves. These ripples in space-time, first detected in 2015, are created by massive cosmic events like the collision of black holes or neutron stars. If a bubble universe collided with ours, it could generate gravitational waves with unique signatures. By analyzing these waves, scientists might be able to identify the presence of another universe. While this is still a speculative idea, advancements in gravitational wave detectors could make it a reality in the future. The idea of bubble universes also raises questions about the nature of our own universe. If we live in one bubble among many, what does that mean for the laws of physics we observe? Could there be universes where gravity is stronger or where time flows backward? These possibilities challenge our understanding of reality and push us to consider that our universe might be just one small part of a much larger, more complex multiverse. Despite the challenges of detecting bubble universes, the search for evidence continues. Scientists are developing new tools and techniques to analyze the CMB and gravitational waves with greater precision. They're also exploring other potential signatures, such as anomalies in the distribution of galaxies or unexpected variations in the fundamental constants of nature. While we may not have definitive proof yet, the pursuit of bubble universes is a testament to humanity's curiosity and determination to uncover the mysteries of the cosmos. As we explore the evidence for bubble universes, we're reminded that the universe is full of surprises. Whether or not we find proof of their existence, the search itself expands our understanding of the cosmos and inspires us to imagine what lies beyond the boundaries of our own reality. Now turning to the conclusion of our exploration, let's take a moment to reflect on the 25 theories about multiverse interactions we've discussed. From the mind-bending implications of quantum superposition and parallel universes to the cosmic dance of bubble universes and the holographic multiverse, each theory offers a unique perspective on the nature of reality. These ideas challenge us to think beyond the confines of our own universe and consider the possibility that we are part of a vast, interconnected multiverse. The diversity of these theories highlights the creativity and ingenuity of scientists and thinkers who are pushing the boundaries of our understanding. Whether it's the many worlds interpretation suggesting infinite branching realities, or the idea of cosmic strings connecting distant universes, each concept invites us to question what we know and imagine what might be. The search for evidence of multiverse interactions is not just about finding answers, it's about expanding our curiosity and deepening our appreciation for the mysteries of existence. As we wrap up, I encourage you to share your thoughts on these theories in the comments below. Which one resonates with you the most? Do you think we'll ever find definitive proof of multiverse interactions? Your insights and questions are what make this journey so exciting. If you enjoyed this exploration of space mysteries, don't forget to subscribe and hit the notification bell so you never miss out on our latest videos. Together, let's keep exploring the wonders of the cosmos and uncovering the secrets of the multiverse. Thank you for watching, and until next time, keep looking.